Hello all, welcome to my course on methods of adhesion measurement theory and practice. Today we are on lecture 22. We are discussing about surface energy, interfacial energy, and the last lecture I discussed about how to derive this Young's equation. So today I will begin by giving a small and simple problem on this Young's equation, how to use that, and then I will start discussing about contact mechanics, but with interaction. So, here is the Young's equation that we derived in my last lecture. So, let us take this small problem here. Let us say that gamma L is 14 millijoule per meter square and gamma 20 S 22 millijoule per meter square. This equilibrium contact angle is 48 degree. So, it is like this. This is here gamma S of this surface, gamma L is of this surface, and we need to find out what is gamma SL here. This is the theta equilibrium contact angle. So, if I just put these values into this equation, then gamma SL is equal to gamma S minus gamma L cos theta equilibrium, and you substitute these values. So, here it is 22 minus gamma L is 14 and then cos of this is 48, and you will get here 12.64. This is just to show you that this Young's equation can be used to estimate the interfacial energy between the solid and liquid, provided we know the interfacial energy between solid, the liquid, and also we know the contact angle, equilibrium contact angle, that is theta. Now, suppose we need to estimate the solid surface energy and we do not know the interfacial energy. So, then we use this Good-Girifaluk equation. So, remember that in the Good-Girifaluk equation we have done it in fact with both the dispersive and polar component. Let us say this is not a polar liquid and we do not need to have the we do not need this polar component. So, we do not have the other part, this Lipschitz van der Waals and then the polar component. So, we do not worry about that. So, let us say that we have therefore this simple equation, and here again gamma L is equal to 28.5 millijoule per meter square and this theta equilibrium is 48. And so, from this model equation, Good-Girifaluk equation, and using this Young's equation, so basically it is a Young-Dupré equation, we get this gamma S is equal to 19.85 millijoule per meter square. We can easily do that. So, that is what we can easily do, and so what you notice here is something like this. This gamma S is let us say I represented by the force in this direction, gamma L, and in this direction and gamma SL. So, in essence this gamma L cos theta plus gamma SL minus gamma S is equal to 0, that kind of defines a force balance at this three phase contact line. Remember, we are talking about all this time we are talking about energy, right, and that is the Young's equation I derived. And now what I am saying is that this equation, as you can see, it is a kind of force balance. So, this is the horizontal component of the gamma L surface energy. So, now it is no longer surface energy, you call it surface tension. So, when you do this force balance, I call it surface tension. So, surface tension of liquid gamma L, surface tension of solid is gamma S, and that of the interface. So, we graduate from interfacial and surface energy to surface and interfacial tension, and this is the horizontal component of the horizontal force balance, horizontal force balance. That is what we have it here. Now, we remember that so what it means is that as if gamma S increases, that means surface tension of the solid increases, that the drop spreads, okay, that we actually see with respect to the liquid if it decreases. On the other hand, if the gamma L increases or gamma SL increases, then the drop retracts. So, for a hydrophobic surface, we know that hydrophobic surface the gamma SL is actually high, gamma L is also high, and gamma S is of a low energy surface. We actually the drop actually there does not spread there. So, this equation which we derived from energy balance actually gives a force balance at the 3 phase contact line, and this is horizontal force balance again the horizontal direction. So, what it means, there is also a vertical direction force balance, but we do not do the vertical direction force balance. Okay. In the vertical direction we will have gamma L sin theta. Now, gamma L sin theta is balanced by the force that is induced by that process in the substrate. So, remember the substrate we have rigid, we have a very rigid substrate, and since it is a rigid substrate, okay, the gamma L sin theta that does not deform it. So, therefore, we do not worry about this vertical direction, the force balance in the vertical direction. However, if any point of time we talk about, let us say, a soft surface. So, instead of being rigid, let us say if it is soft, okay, then what we will see that the surface, the vertical component of the surface tension of the liquid, that will cause a deformation in the solid over here. Okay. At that time we have to worry about this the vertical component of the surface tension as well. Okay. Otherwise, in most common problems in which the substrate is solid, it is quite rigid, solid substrate is rigid, in that case we do not need to worry about this vertical component of the force balance. There is another idea that we often will use, and we use in different contexts. So, that is about pressure difference across the curved interface. So, let us say this is that curved surface interface between separating two different materials, and this has got the radius of curvature in two perpendicular planes r1 and r2 respectively. So, the total surface curvature of this surface is given as 1 by r1 plus 1 by r2 multiplied by gamma is the surface tension, and that will give this pressure difference across this interface. So, pressure below this particular material interface is P1 and that above is P2. So, P1 minus P2 will be given by this. So, suppose that we have got in the capillary problem we have got it is something like this, the meniscus was something like this, and in that case let us say this is a circular capillary, capillary is a circular cross section, and then this is the meniscus, and let us say that this is a wetting liquid. So, the angle theta is almost equal to 0. So, what we will see there is the pressure difference. So, the pressure here is P1, let us say pressure here is P atmosphere. Okay. So, in that case what we can show is that the P atmosphere is greater than P1, that is why meniscus goes down over here, and in that case this P atmosphere minus P1, and that will be given by this gamma, and then the radius of curvature is same in both direction. In one is this particular plane, another is this plane, one is this plane, another is this plane, both the sides it is same because this contact angle here is 0 degree, and so therefore this is actually 1 by r plus 1 by r, where r is the radius of curvature, radius of this particular capillary. So, it will come out to be 2 gamma over r. Okay. But remember the meniscus, this is a wetting surface. So, therefore, the meniscus is concave here. Had it non-wettable surface, the meniscus would have been convex there, but it is concave here. So, therefore, it is like this, P atmosphere is greater than P1 and the meniscus goes down like that. So, this is all I wanted to talk about the surface tension of liquids and its effects, and there are many other things to talk about, but in our course we do not need all that topics. So, we will like to now go to our next topic, which is about indentation of an elastic half space with interaction. Remember that so far we have talked about the indentation without interaction without any adhesion, and we have now discussed little bit about the adhesion. So, now we will combine these two ideas, and that is actually the objective of this particular course. So, before I start about that with interaction, so let us go back to Hertz contact mechanism that we had discussed a few lectures back, and here we had basically two spheres in contact. Let us say two spheres in contact. Okay. Their radii of curvature are r1 and r2, elastic modulus Young's modulus was E1 and E2, Poisson ratio was sigma 1 sigma 2. Remember that it was something like this, that we have got let us say one spherical one sphere here, and there is another sphere there. So, it was something like this, right, and let us say that in one case this was R2, another case this was, sorry about that, this was let us say R1 like this. So, now there are contact pressure is P0 and this is contact pressure is P0. So, what happens? What happens is that you apply some contact pressure P0, the contact area or the radius of the contact area that increases from 0 to some finite value A0, and this A0 is given by 3 P0 into R by 4 E star to the power 1 by 3. So, we derived this equation, okay, by using that Hertz contact mechanics, and then he had few assumptions there, the frictionless contact in one of them, this A0 is much smaller with respect to the R, that is another. So, that the elastic half space problem can be used, okay. Hertz used the results of elastic half space, and for that he had to make these assumptions. So, here remember this 1 by R will be given as this is the mean relative effective relative radii of curvature 1 by R1 plus 1 by R2, and this effective modulus is like this 1 by E star is given as like 1 by sigma 1 square plus 1 E1 by 1 minus sigma 2 square by E2. So, sigma 1 is the Poisson ratio, and in many cases we actually write another notation K, capital K, we write it here 4 E star by 3. Okay. So, we replace 3 by 4 is by 3 K by 4, that also we do, we have done that just to make things little more compact, that is it. So, now what happens when there is the interaction between them? So, what we expect is that when there is adhesion between them, then whatever is the contact area that is achieved by this without adhesion, that should increase, because now there is interaction between them. So, the contact area will achieve or will increase from this A0 to some other finite value. So, that is what we will like to understand, how much is that. Now, in order to do that, we have to in order to know that how much this contact area will increase. So, let us say it increases to something like this. Now, it is something like this, let us say. So, the contact area has increased now from A0 to, let us say this is now A1 now, okay, like that. So, in order to know that how much this contact area is increased and how to relate that to the energy of adhesion. So, now we know that we call it this work of adhesion, okay, how to relate that. So, in order to do that, we have to consider that what happens when we apply this contact pressure capital P0 over here, what kind of pressure distribution that happens at the contact line. Now, when there is no interaction between them, then the contact pressure or the pressure distribution can be given as like this. This is the Hertz contact pressure that we have derived earlier. P of P as a function of R will be P0 into square root of 1 minus R square by A square, and where we have also obtained this relation with respect to total pressure applied as like this, small p0 is equal to this quantity. So, which is a function of the radius and the Young's modulus of this material, and the radius is also relative radii of curvature, and this E star is the effective Young's modulus. Now, what we have done in order to get this radius of contact A, we have actually pushed this particular point of application by a distance delta, and the delta is given by like this, delta is given by this particular equation here, that also we have derived. We have also derived that this expression A here, and A is equal to 3 P0 by 4 E star to the power 1 by 3. So, that also we have derived, and finally, we have derived also, if I substitute the expression for P0, okay, into an A and all that from here, if we substitute it, okay, we will get this expression. So, A is equal to square root of R into delta. So, delta is again that is the distance, deforming distance through which these spheres have moved towards each other. We have discussed all these things in last few lectures. So, now we will now consider, so let us say over here. So, now since we are applying the P0, so initially we had the contact area, this A over here, and these are the pressure distribution, okay, at the contact area. This is the Hertz pressure distribution that I already said, and this is the total deformation V1 by V2, and so over here. Now, now we do not consider for the when you consider this Hertz pressure distribution or the contact of these two spheres, okay, we actually did not consider, remember we did not consider this particular kind of pressure distribution. Okay. Now, this particular pressure distribution that is observed when, now when we have got elastic half space and we have got a flat punch like this. Remember that when you have flat punch and we apply a load on it, okay, let us say some load P dash, let us say, and then this elastic half space that actually deforms like that. So, it is happen something like this. So, since it is a flat punch, so the deformation that remains constant all through, right. So, this does not vary with respect to r. So, this remains constant, that is the way, because it is a flat punch on like that. So, in that case the pressure distribution within this region is given by like this. So, there is this singularity that happens at the r is equal to a that we have talked about earlier. So, it is when there is no interaction between them, we do not need to consider this particular pressure distribution because of couple of reasons. One is that if P 0 is positive, okay, then there will be interference outside the contact area, which is not required because then there will be because of this particular singularity, okay, there will be problems. We do not need that, that is not going to help us on this positive P 0 dash interference outside the contact area. And if it is negative, P 0 is dash is negative, then there is infinite tension outside the contact area, because here in this region there is infinite because it is singularity there. So, in a sense that when we do not have an interaction, we do not need this particular, this particular pressure distribution actually is not there. But however, situation changes when we have the interaction between them. So, when there is interaction, then the pressure distribution changes because there is attraction between these two material, and so as a result when without adhesion, okay, these two surfaces were making contact here like this. Now, there is interaction between them, attraction between them, they actually contact by 90 degree here like that, okay, because there is attraction between them, and so this additional contact area as a result appears. From at the load P 0 itself, the contact area is no longer A 0, it is actually A 1 now. So, actual contact area increases from A 0 to A 1, and since there is attraction between them, there is a tensile stress that develops at the vicinity of the edge of the contact area in this region. So, here there is compressive stress within this region and this tensile stress in this region, and so therefore, we consider in this region the pressure distribution, okay, 1 minus square root of 1 minus r square by a square, and in this region, okay, we consider the pressure distribution as P 0 dash, and here it is 1 minus r square by a square root of 1. So, this is at the denominator now. So, that is the way okay, the pressure distribution that occurs, and so the total pressure distribution, overall pressure distribution is given by this. So, see this portion, okay, this quantity, this part of the pressure distribution that does not alter, that does not change the contact radius, okay, because that remains constant. On the other hand, this changes the stress, it leads to the stress singularity, okay, at the crack tip or at the contact line. So, this contact line stress singularity that is not a problem because this particular material or of the two spheres that deform over here, and that creates some finite radius of curvature, and because of this deformation it generates the elastic stress, and that goes against this stress singularity of the pressure distribution, okay, the opposite direction. So, that way it mitigates. In any case, we will like to know that what is the energetics of this system. So, what I was trying to see is this, that given some amount of adhesion, work of adhesion between these two spheres, okay, and an application of some load, this capital P 0 over here, what is the contact area A 1 that will be attained. That is what we will like to figure out, and that we will like to do by this energy minimization, once again by energy minimization. So, it is something like this. You have got, let us say, one surface with the surface energy gamma 1, another surface energy gamma 2, and now you bring them together. So, you have the interfacial energy gamma 1 2. So, the excess energy or the work of adhesion, this is called, this is actually gamma 1 plus gamma 2 minus gamma 1 2. So, thermodynamic work of adhesion. Okay. So, here when you consider this the contact mechanics with adhesive interaction, we have to consider this particular energy, effect of this particular energy. So, that is the crux of the matter here. So, this quantity, that gamma 1 plus gamma 2 minus gamma 1 2, this is called the work of adhesion. Work of adhesion means that, you know, suppose you have this interface, okay, which has energy gamma 1 2. Now, when you try to separate it, you create two different surfaces, one here, another here, and so because of this new surface that you create, so there is a new amount of energy that needs to be given, that is will be this gamma 1 plus gamma 2 minus gamma 2. It is from that concept this work of adhesion, this idea comes, and this is the thermodynamic work of adhesion, because this is a intrinsic property of the surface. So, here also I have gone through that if the material instead of vacuum it is a different material, then this W 1 2 3 will be given by this equation. We have actually gone through this. So, now we will first consider the pressure distribution P r is equal to this, and for that we have already estimated the expression for vertical displacement, okay, at any point, which is given by this particular equation, and delta is equal to s. So, we have derived this. So, deformation delta because of this load, that also you know. Now attractive forces between the surfaces, the contact radius in equilibrium will be greater than a 0. So, we like to relate a 1 in terms of applied pressure P 0. So, now what exactly it means is this. In essence, what I am doing is something like this. Let us say that this is P axis, let us say this is A here. So, let us say that this A depends upon P. So, remember this depends upon 1 by 3, A depends relate to, this is A relates to P 0 as to the power 1 by 3, right. Yeah. So, it will go as it is P 0 to the power 1 by 3, right. It goes as like this, 3 P 0 by 4 E star to the power 1 by 3 here, right. Now, so here let us say this is my this is the kind of relation like that, A goes as P to the power 1 by 3. Let us say that the pressure here is P 0. So, this is the A 0 that you would have achieved over here, but at this particular load, because of the interaction, it achieves this particular radius, that is A 1. The way that we will do is something like this. So, we will remember that this is an equilibrium position at which this it reaches this A 1. So, why it does not matter that it is a path independent. So, let us say that we have this increase the pressure. So, increase the pressure at the contact pressure goes to P 0, and then let us say it goes to contact pressure, that is P 1. So, at contact pressure P 1, this is Hertz contact pressure. So, this P 0, this is actually Hertz pressure, this line is Hertz contact mechanics, right. Now, we increase the pressure from 0 to P 0 to P 1. So, the contact radius now is over here, right. This is A 1, and now let us say I decrease the pressure. So, this is a fictitious pressure that I have attained P 1. Now, I will decrease the pressure to P 0 over here. Remember that in the in that other pressure distribution, okay, in which we have this the radius of contact remains constant, okay. Here the pressure distribution, okay, for this particular case, this is P 0 dash divided by 1 minus r square by a square, okay, 1 for this case, okay. The radius of contact that remains A remains constant. So, A remains constant at A 1 here, and we decrease the pressure, okay, from this P 1 to P 0, because finally we have P 0 here and A 1 here, that is all. So, we have to reach this point. So, what we will do is we will like to find out that what is the total energy, elastic energy, that is spent in taking this particular contact radius from 0 to A 1 by this method. So, first by Hertz contact mechanics, or Hertz pressure, we have increased the pressure from 0 to P1 to this particular point, and then we have decreased the pressure to P0 using this mechanism. Okay, I hope you follow it. So now, in order to do that, what is the energy that is spent in taking this contact from 0 to A1, that is what you A1 by this. So, from 0 to pressure, to take the pressure from 0 to P1, that we will see. So, remember that A1 is given by this quantity 3 P1 by R by 4 E star, right. So, this is that. Yeah. So, now what is the energy that is required to take this increase the pressure from 0 to P1. So, that can be given as E1 into P of d delta. So, delta goes from let us say 0 to delta 1, and let us say this P1. So, the P this at delta is equal to delta 1, okay, the P reaches P1, okay, that is all it means. So, this is the P into delta, the force into distance, that is the energy, basically that. So, here what is delta over here, that needs to be known. So, that is actually known over here. So, delta is given by this is the from the Hertz mechanics that we know. So, delta is equal to 1 by r 3 p r 4 I square square root of 2 by 3. So, so I told you that we will like to write this k capital K, introduce a notation here, that is 4 E star by 3 is equal to capital K, and so therefore d delta will be written as derivative of this with respect to p, and so it becomes 2 by 3 p to the power minus 1 by 3 into dp, and you multiply it by dp here. So, p d delta will be like this. So, p d delta is given as, now let us say 0 to p1, and this is 2 by 3, this is p to the power 2 by 3, this is capital K to the power 2 by 3 r to the power 1 by 3 into dp here. So, this will be 2 by 3, and here let us say this is k to the power 2 by 3 r to the power 1 by 3, and so it will be 2 by 3. So, it is 2 by 3 plus 1. So, 1 by this is 2 by 3 plus 1, and this is p to the power 2 by 3 plus 1. So, this will be 5 by 3. So, this is 5 by 3. So, it is 2 by 5 into 1 by capital K to the power 2 by 3 r to the power 1 by 3, and this is goes from 0 to P1. So, it is P1 to the power 5 by 3. This is the energy stored on the first portion, that is U1. In order to calculate this U1, so the pressure, so the energy stored in these spheres to take the pressure from 0 to P1, that is this quantity, right. And then let us say that we have to take it down from P1 to this quantity P0 here. Yeah, so it will require some time. Yeah, so I will take up this analysis once again in the next lecture. Thank you.